For millennia, humanity gazed at the stars and wondered, are we alone? Is Earth unique? That profound question ignited a scientific revolution, the hunt for exoplanets. Worlds beyond our solar family, orbiting distant suns in the inky blackness. These aren't mere points of light anymore. They are alien landscapes we're just beginning to map. Imagine fiery lava planets, water worlds deeper than any ocean, gas giants denser than iron, and puffy planets lighter than styrofoam. This isn't science fiction. This is the exhilarating reality of modern astronomy, unfolding right now. So, what defines these exotic wanderers? Officially, the International Astronomical Union calls them exoplanets or extrasolar planets. They must orbit a star, or even a failed star called a brown dwarf, or the burnt-out core of a dead star. Crucially, they can't be too heavy, staying below the mass where nuclear fusion kicks in, about 13 times Jupiter's mass. Think of them as cosmic Goldilocks objects, not too big to be a star, not too small to be something else, orbiting a central anchor. The breakthrough came surprisingly recently. In 1992, astronomers cracked the code, confirming the first exoplanets ever detected, whirling terrifyingly fast around the corpse of an exploded star, a pulsar. But the real game changer arrived just 3 years later, in 1995. Picture this, the first exoplanet circling a star, a main sequence star called 51 Pegasi. This discovery, a blistering hot Jupiter hugging its star impossibly close, shattered our solar system-centric view forever. It proved that other suns have families of planets, and those families could be wildly, unimaginably different from our own. Fast forward to today, late June 2025. The cosmic census has exploded. Astronomers have confirmed a staggering 5,926 exoplanets, residing in 4,419 individual planetary systems. Almost 1,000 of those systems are bustling neighborhoods, hosting multiple planets. And this number is rocketing upwards daily. Think about that scale. Based on these discoveries, we now estimate our Milky Way galaxy alone could be teeming with anywhere from 100 billion to 300 billion planets. Even more mind-blowing, roughly 1 out of every 5 sun-like stars might cradle an Earth-sized world within its Goldilocks zone, the habitable region where liquid water, that vital ingredient for life as we know it, could exist on the surface. Expand that to include planets orbiting the abundant faint red dwarf stars, and the estimate soars to a breathtaking 40 billion habitable Earth-sized worlds just in our galaxy. How do we find these incredibly distant faint worlds lost in their star's glare? Not by snapping direct pictures, that's immensely difficult. The vast majority, about 74% of all discoveries, that's 4,389 planets, owe their detection to the transit method. Imagine a tiny ant crawling across a powerful spotlight. That's essentially what happens. We meticulously monitor a star's brightness. If a planet passes directly in front of it from our viewpoint, it causes a minuscule telltale dip in the starlight. NASA's Kepler and TESS missions, dedicated transit hunters, have been powerhouses in this field. Another crucial technique, responsible for about 19% of finds, 1,128 planets, is radial velocity. Picture a star doing a tiny rhythmic dance. The gravity of an orbiting planet tugs its star, causing subtle shifts in the star's light spectrum, a Doppler shift we can detect. It reveals the planet's presence and hints at its mass. The diversity already uncovered is staggering. We found the scorched remnant core of a gas giant stripped bare, planets where diamond might rain from the sky, and entire systems like TRAPPIST-1, a dim red star orbiting Earth-sized rocky worlds, several prime candidates in the habitable zone, offering incredible laboratories for future study. We know our closest exoplanetary neighbor, Proxima Centauri b is a mere 4.2 light-years away. We've found planets orbiting double suns, Kepler-16, witnessed tiny worlds like Draugr, only twice the mass of our Moon, and uncovered hidden giants like Kepler-139f, its presence betrayed only by the gravitational nudges it gave to other planets in its system. Just recently, an international team combined data from the Gaia satellite and the powerful ALMA telescope to spot a massive infant gas giant 3 to 10 times Jupiter's mass, still deeply embedded in the swirling dust disk around the young star MP-MUSS, a pioneering glimpse of planet formation in action.
So, we know the transit method is our most prolific planet hunter, responsible for the vast majority of those nearly 6,000 confirmed worlds. But how does this cosmic detective work function? Imagine staring intently at a distant lighthouse, miles away on a dark shore. Now, imagine a tiny moth flitting directly across its blinding beam. From your distant vantage point, the lighthouse's light would dim ever so slightly, almost imperceptibly. For the brief moment, the moth blocks a fraction of the beam. That's the core principle. We watch a star, and when an exoplanet passes directly between that star and our telescopes, it blocks a tiny sliver of starlight, creating a miniature, predictable eclipse. This dip in brightness is incredibly faint, often less than 1%, sometimes just 1/100% for an Earth-sized world around a Sun-like star. Detecting this requires instruments of astonishing sensitivity, orbiting above Earth's shimmering, blurring atmosphere. NASA's Kepler Space Telescope pioneered this hunt, staring unblinkingly at one dense star field for years, amassing a treasure trove of light curves, graphs tracking a star's brightness over time. Its successor, TESS, the transiting exoplanet satellite, scans nearly the entire sky, hunting for these characteristic dips around the brightest nearby stars. What secrets does this fleeting shadow reveal? Crucially, the depth of the dip tells us the planet's size relative to its star. A deeper dip means a larger planet blocking more light. The duration of the dip reveals how long it takes the planet to cross the star's disk, hinting at its orbital speed. And critically, the time between consecutive dips tells us the length of the planet's year, its orbital period. Combine this with the star's known properties, like its mass from stellar models, and we can pin down the planet's orbital distance. Suddenly, that tiny flicker tells us world size, orbital period, and distance from its sun. But the transit method holds even more power. During the transit, a tiny fraction of the star's light filters the planet's atmosphere, if it has one, on its way to our telescopes. By splitting this filtered starlight into a spectrum using instruments like those on Hubble or the revolutionary James Webb Space Telescope, astronomers can detect the unique light signatures of molecules in the alien atmosphere. This is, see a dip in specific wavelengths? That's the fingerprint of water vapor absorbing light. Another pattern? Sodium. A characteristic signature? Carbon dioxide or methane. This is how we've detected water vapor on planets like the Neptune-sized HAT P11b, sodium and potassium in the atmosphere of the blistering hot Jupiter WASP-96b, and even potential evidence for carbon dioxide and methane in the air of the rocky world K218b. It's our first tantalizing breath of alien air. Yet, it's not without challenges. False positives abound. A grazing eclipse by a companion star or even large star spots rotating into view can mimic a planetary transit signal. Confirmation often requires multiple transits observed, supporting evidence from another method, like radial velocity. And the geometry is crucial. Transits only occur if the planet's orbit is aligned edge-on from our perspective, a relatively rare alignment. Despite these hurdles, the sheer power of staring relentlessly at vast fields of stars has delivered wonders. The compact, potentially habitable TRAPPIST-1 system, whose 7 rocky worlds all transit. The confirmation of Kepler-186f, one of the first Earth-sized planets found in a habitable zone. And the thousands more awaiting detailed atmospheric scrutiny by Webb and future giants like ESA's Ariel mission. dedicated to probing the chemical makeup of exoplanet skies. The transit method is our most successful eavesdropper on distant solar systems, transforming the faintest flickers of starlight into revelations about alien worlds. But how do we find the planets whose orbits don't bring them directly across our line of sight, or those too distant or faint for their transits to be easily seen? Our cosmic toolkit holds another indispensable instrument.
So, we've seen how transits reveal planets that cross our line of sight. But what about the vast majority of worlds whose orbits tilt away from us, never casting a shadow we can see? Or those giants lurking far from their stars, taking decades to complete an orbit? For these cosmic wallflowers, we turn to an ingenious technique that doesn't rely on planetary shadows, but on the star itself. Imagine, if you will, not watching the lighthouse beam, but listening to the lighthouse keeper whistling a single pure note. If the keeper starts walking towards you, the pitch sounds slightly higher. Walk away and the pitch drops lower. That's the Doppler effect, the same phenomenon that makes a race car's engine whine rise as it approaches and fall as it zooms past. Now picture a star and its planet. While we often say planets orbit stars, the truth is more elegant. Bodies orbit their common center of mass. That means the star doesn't sit perfectly still. It executes its own tiny rhythmic dance around this shared balance point. When the star wobbles Earth, its light waves get squeezed slightly, shifting towards the blue end of the spectrum. As it wobbles this way, the light stretches, shifting towards the red. This is the radial velocity method, detecting these incredibly subtle color changes, these stellar blue shifts and red shifts, to reveal the unseen planet tugging its parent star in a gravitational waltz. Measuring this stellar wobble is an extraordinary feat. For a massive planet like Jupiter orbiting a sun-like star, the star's velocity change is only about 12 meters per second, walking pace. For an Earth analog, it's a mere 9 per second. Detecting shifts this minuscule requires instruments of breathtaking accuracy, high-resolution spectrographs like HARPS in Chile or NEED in Arizona. These machines act as cosmic speed guns, splitting the star's light into an incredibly detailed rainbow spectrum and hunting for the telltale drift of dark absorption lines, the unique chemical fingerprints embedded in the starlight. The key clues? The F of the Doppler shift tells us the planet's minimum mass. A larger velocity wobble means a more massive planet exerting a stronger gravitational pull. The F of the rhythmic shift, the time it takes the pattern to repeat, reveals the planet's orbital period, its year. And crucially, unlike transits which need a specific alignment, radial velocity works for planets orbiting at angle relative to our view, vastly expanding our hunting ground. It was this method that brought us the very first confirmed exoplanet around a sun-like star, 51 Pegasi b, a hot Jupiter defying all expectations by orbiting its star in just 4 days. Radial velocity excels at revealing the architecture of planetary systems. Multiple sets of periodic wobbles, each with their own rhythm and intensity, betray the presence of multiple planets tugging on their shared star. This is how we unravel intricate systems like GJ667c, host to multiple potentially rocky worlds in its habitable zone. But the method's power extends beyond mere detection. By precisely mapping the star's velocity changes over the planet's entire orbit, astronomers can infer the shape of that orbit, whether it's nearly circular or a stretched ellipse. And here's the critical synergy. When a planet found via transit, radial velocity provides the missing piece we get from the light dip alone, the planet's actual mass. Combine the mass from radial velocity with the size from transit, and we unlock the planet's density, the golden clue to its nature. Is it a puffy gas giant, a dense rocky super-Earth, or a water world? Density tells the tale. This one-two punch of transit and radial velocity has characterized thousands of worlds.